Okay, now, good afternoon. Now here, today we'll be looking at torsion. Okay, torsion. Now here we have some notes here. I have some notes here. So torque is an important concept of physics that helps us to understand how things happen around us. With the help of torque, it can be determined what the direction and magnitude of a rotational force applied on an object is, allowing you to access the results that may be generated. Generally, torque can help us to determine whether the force applied will result in counterclockwise or clockwise motion. Not only that, it can also help you predict the angular acceleration from which the object is being rotated. So that is torque. So that is the agent of motion for anything that is moving in circular path or rotating. So now here I have 4 examples of applications of torque. Okay, so you can go through this, and then we have this, that is the torsional spring, or we can call it as the helical spring, torsional spring. Now first thing is turning moment. So here we have the definition of turning moment. So turning moment, that is torque. Okay, torque is defined as the product of tangential force to the distance d about this point O here. Look at my laser pointer. Look at the laser pointer. So you can see the force F. Force F is here. So the line of action of the force F is being 90 degrees to this, the distance here, which we called it as the radius, because when you turn this, it will move in a circular path. So when it moves in a circular path, then of course this we can call it as a radius or a distance, which is about the point O. So that is turning moment or torque. So the failure of any objects or shaft due to torque is called torsion. So torque applied to shaft produces shearing stresses. Torque that is applied to shaft will produce shearing stresses on the faces perpendicular to the axis. So remember, shearing and area, they must be parallel to each other, okay? Also known as torque is also known as moment of force, or simply moment torque, or simply moment or torque. Refers to the rotational force to rotate an object about a pivot or fulcrum axis. The concept of torque is very similar to the force, meaning that force is all about pushing and pulling an object, while torque is something that causes an object to twist or rotate. Torque is dependent on several things. 1, the magnitude of the force, that means the magnitude of this. Okay, so how many newtons is that? Or how many kg of force is that? And then the distance between the point of the force of application and the rotation axis. This is the point of the application, and this is the rotating axis. So it also relies on this distance. So torque is a function of this value, and of course this distance here, which is about the rotating point, the rotating axis. Okay, so then the next part here. So now this is an example when a shaft is subjected to turning moment or torque. So let's say point A is fixed. Point A is a fixed point. The shaft, which is attached to the wall, okay, and then point B is another point that is located at the circumference of the surface, cross-sectional surface of the shaft. So when you apply torque, what happens to point B is it will be slightly angularly distorted. Okay, it will be slightly angularly distorted about point A. So you see the next diagram here. So this is your point B. So when you apply torque, the T. So what happened is, so B, this plane AB here will be distorted to another one of this line here, the blue line, okay, which is, you can say it is actually angularly twisted or displaced. So that should be your B prime. Hope you can understand how the thing is being twisted, where this point is fixed. Look at my laser pointer. This point is fixed. So when you apply a rotating torque or a tangential force onto this surface, point B will be displaced to B prime here. So this is an example of a shaft that is being twisted. So this angle here, we let it be equals to a gamma. Okay, the angle of twist, and this will be the length. This will be the length. So either AB or AB prime is the length of the shaft. So it's denoted as L, the length of the shaft. So when you apply torque, so B, the point B will be angularly displaced to B prime, the blue point. So, and at the same time, other than along the length, it is being angularly twisted for gamma. Here on the surface here, you have another angular displacement, that is theta. That is theta. Okay, so now when you refer to this, okay, from this point here, from my laser pointer, the center point of the shaft, to point B, or from the center of the shaft to point B prime, this is a constant. This can be the radius of the shaft, the cross-sectional of the shaft, the radius here. So what is the displacement of this arc here, B to B prime? What is this angular displacement here? This angular displacement here can be determined by taking the radius multiplied by this theta here, r theta. Arc length is equal to the product of r, the radius, to the angle theta. Or you can also take this, the arc length of B to B prime also can be equals to the length of this L to the angle gamma for this arc length here, for this arc length. Okay, so you can calculate this arc length either by taking radius times or multiply by theta, or this length here of the shaft multiplied by the angle gamma. Okay, so the arc length actually can be written as either as r theta, that means this radius here to this angle, okay, or you can take the length L to the angle gamma, that is arc length. Okay, because we know that arc length is directly proportional. This arc length actually is directly proportional to this angle theta or this angle gamma. So the constant will be either the length or the radius. Because when you say arc length is directly proportional to theta, then there should be a constant. So that is the radius for this surface. And along the length, if you say this arc length is directly proportional to this angle gamma, then the constant should be the length of the shaft. So that is r theta equals to L gamma. So when you rearrange this, okay, so you have this, and then gamma will be equals to r times theta over L. And we know that gamma is actually the shear strain, And since this is the shear modulus, hope you still remember, this is not Young's modulus, this is shear modulus, equals to stress over strain. The only thing the stress here is a shear stress, and the strain is known as the shear strain. So by putting in your gamma equals to shear stress over shear modulus, to this gamma equals to r theta over L, that is from here. Okay, so you substitute your gamma this into this formula, so you will get this equation: tau over G equals to r theta over L, or again rearranging this, you will get shear stress over radius r is equal to the product of shear modulus to the angle of twist divided by the original length of the shaft. This is one of the formula which you should remember. Okay, then the next part here, the stress. Now anything that is subjected to torque or turning moment, we say it is subjected to a shear stress which is parallel to the surface of the shaft, cross-sectional surface of the shaft. So let's say this is the surface of the shaft, the cross-sectional surface of the shaft, and let us consider one tiny element, an elementary ring with a thickness of dr, with a radius of r for internal and an r for the external, the radius, the total radius. Okay, so the shaft cross section. So the force set up in each element. What is the force that is acting here? We know that shear stress equals to force over area. Stress equals to force over area. So force is equal to stress times area. Okay, force is equal to stress times area. So the stress due to torsion, due to torque, due to turning moment, is what we have is the shear stress. And the area here, remember, for any shear stress or any shearing force or tangential force, area that we consider should be on the same plane as the shear stress. So that means parallel. So the area that you have to consider is the area of this elementary ring here. So what is the length of this? What is the circumferential length of this elementary ring? So you can take as 2 pi r. And then for the area, then you need to multiply by its thickness, dr. So you have this. And this is equals to a force only, actually. A force. So you can consider that df, a force, okay, acting on the elementary ring. Now this force will produce a moment. When we say moment, that means you have the force, for example, a force here acting here. Okay, then multiply by the radius, you will get what we call torque, the turning moment. Okay, the turning moment. So turning moment or torque is defined as what? Tangential force multiplied by the radius. Now the tangential force that we have here is the shear stress times 2 pi r dr. So put it in and then times radius. So 2 pi r dr, shear stress times 2 pi r dr here is actually what you have here. This is the force. This is the tangential force. Let's say you have a force here like this. A tangential force acting on the elementary ring. Okay, so put it here and then multiply by the radius till you get the torque transmitted by the elementary ring. So that is why I put dt. So you have this r times to it, so you have r squared. Then and we know that shear stress over r is equal to g theta over L from the previous slide. Then shear stress is equal to radius g theta over L. So the shear stress here, this whole thing here, you can substitute into this. Yeah, over here. See my laser pointer. So you have this. Okay, so now what you need to do is to find the total torque. So to find the total torque, that means you must integrate both sides. The left hand side you have to integrate with respect to t, and then this side you have to integrate with respect to r. Okay, so r times this r here, so you have r cubed. So you have this equation, then integrate for the total torque. So you have this. So it starts from 0 to radius r. So you twist, you turn. So that means you must have a torque from here to here, the distance, for the force multiplied by this distance in order to produce a turning. Okay? So you have this. So integrate integrate. Okay, after integrating already, substitute everything, then you'll come to this equation. The final equation is here. So you have 1, and the previous one is which one? Previous one is this, right? And now you have this. So can you see? This and this. So based on this whole equation, based on these two parts, this one and this one, so you have an equation like this, which we call this as the simple torsion equation. The simple torsion equation. T is the torque, J is the polar second moment of area, tau is the shear stress, R is the maximum radius, G is the shear modulus, theta is the angle of twist, and L is the original length. Then for this equation here, we cannot simply use this equation like that. So we usually break this up into a strength relationship. This formula you should use if you want to calculate the strength, or this formula you should use whenever you want to calculate the stiffness. So this equation here actually is broken up into two parts. Okay? One is strength relationship, the other one is stiffness relationship for your calculation work later on. Okay, so this is to teach you how to find the polar moment of inertia or the second moment of area about z-axis, y-axis, and x-axis. This you should refer it at home, and this you should have done it in your engineering maths application. Okay, so finding out the moment of inertia or the second moment of area. But for the time being, okay, we just need to remember the formula. That is this for the polar moment of inertia. That is for a disc. So for a solid shaft, you have this. So Izz, that means the turning about the axis here. The turning of the disc here. Look at my laser pointer. About this axis. Okay. So you have the polar second moment of area. For a solid disc is this. You can change this to r power 4. Then it should be divided by 2, not 32 anymore if you change this to radius. So this is Izz. So you can also find Ixx and Iyy by taking theorem of perpendicular axis, also which you have studied in your engineering maths. Okay. So this is actually basically your shear stress distribution diagram. So based on these diagrams here, we can say, okay, shear is maximum when the radius is maximum. So when you refers to this radius here, from this point to this point is your maximum radius. So also on this surface here, the shear stress is maximum. But when you refer to this point here, okay, your radius is 0. So your shear stress also at this point should be equal to 0. So that means your shear stress, maximum or minimum, it really depends on whether you are looking at the radius, the inner radius or the outer radius. Remember, outer radius always will give you a greater shear stress, and the inner radius always a smaller shear stress. So that is why we can write a relationship between shear stress and the radius in this format. Okay, or in other words, you can also say because okay, this g theta over L is actually a constant. G is a constant. Theta you can consider as constant per unit length. Okay. So that is why you can have this equation. Okay. So thank you for the class. Thank you for listening today. Thanks a lot. Subscribe please and like. Thank you.